Okay, so welcome to the second session of today. It's a great pleasure to introduce Gebhard Martin from Bonn. He'll tell us the characteristic P story, which is automorphisms of the Pezzo surface and positive characters.
Yeah, thank you very much. Thanks for the invitation. Thanks for setting up this room. So I apologize because I think this will be the only time you will see me in this talk, but I have to sit down. Otherwise, I can't do it.
I'll point it to you.
Okay, very good. So I'm going to talk about automorphisms of del Pezzo surfaces in positive characteristic. This is joint work with Igor Dolgashev. This is a very classical topic, I guess. It has a small twist that's in positive characteristic as well. Can you hear me properly, by the way, or am I too quiet? Okay, very good. Okay, see you later. Okay, so I'm working on an algebraically closed field. And for me, P is always the characteristic. Okay, so this is a story about del Pezzo surfaces, and let me just recall this very quickly. Yeah, so it has a bit of a delay.
Sorry.
Anyway, so
I'm trying to just enlarge you. Just one more. I will. Yeah.
Maybe I can also make this bigger. Okay. Very good. Okay, so so let me recall some facts on del Pezzo surfaces. Okay, so a del Pezzo surface in this talk, so they will be smooth. And let me recall, I want really del Pezzo, not weak del Pezzo or something like that. So I want minus kx ample. And there are 10 deformation types of those. And we can distinguish them as follows. So let me denote by d the degree. So a del Pezzo surface is either P1 cross P1, right? Or a blow up. Of P2 in 9 minus d points in general position. Okay, so recall just quickly, general position means all of them are distinct, no 3 on a line, no 6 on a conic, and no 8 on a singular cubic, such that one of them is a singular point. Okay, I will not write this. In particular, all of those del Pezzos that are not P1 cross P1, they're blowups of P2, right? And in particular, this d, the degree, is between 1 and 9. Okay, and then you have those two families of degree 8, and you have the 9 other families. Okay, the main result I want to talk about a classification of all groups that can act on del Pezzos. Or that can occur, say, as automorphism groups of del Pezzos. For X del Pezzo of degree d. And this is a bit vague, but a description of the surfaces that realize the groups. Description of the surfaces that realize G. Okay, and as I said, this is a very classical topic of overseas. I have to write a lot of names now. So let me write classical if P is equal to 0. And the names I should write, but no, there's no space. So maybe let me say them orally. So I guess one of the first people who did this was Bertini. It was also studied by Castelnuovo, Cantor, Wyman, was Segre, Rousseau, and then there was Jeremy Blanc who classified the abelian groups that act. And then the classification was finished by Dolgashev and Iskovsky in characteristic 0. all groups. No, all groups, yes. But only the groups that appear as automorphism groups of Del Pezzo, so not the conic bundles. Okay, so this is classical if P is equal to 0, and I will tell you in a moment that if the degree is at least 5, this is very easy. So easy if D is at least 5. And then there was work of Dolgashev and Duncan a couple of years ago who did this in degree 4 and 3. And then our contribution is the remaining degrees 2 and 1 in positive characteristic. Okay. Okay, and why should you care about this kind of result? It's because, well, first of all, the geometry of those surfaces, we saw them many times this week, right? It's very important, and it's very nice geometry somehow. So I think this is interesting on its own. But if you're more interested in Cremona groups, then this is also an important part. Okay, and I think we also have this mentioned this week already. This because for every finite group G, there exists a bijection between conjugacy classes of embeddings of G into the Cremona group of rank 2 over their field. Okay, so this is up to conjugacy. And there's a bijection with pairs X rho, where X is a rational surface. And G acts biregularly on this surface. Okay, and this is up to equivariant birational transformation.
Can you make it an equivalence of Cat?
I haven't thought about it. But the main point I want to make here is now on the right hand side, right, you have rational surface, G action, and then you run a G equivariant MMP and you go to the minimum models. Turns out the minimum models you get are Del Pezzo surfaces and conic bundles, G minimum models. Okay, so if X rho is minimal, then X is Del Pezzo or conic bundle. Right, and the important part for this is really that the group is finite. Okay, so you could say, let me write this, that determining odd X for X Del Pezzo is the first step in the classification of finite subgroups of the Cremona group, rank 2. Okay, and well, I said this before, that this classification of groups that can act on Del Pezzo surfaces in characteristic 0 was finished by Dolgashev and Iskovsky, and their goal was the classification of finite subgroups of the Cremona group. This is also the title of the paper where this appears, and this was done in 2006, I think. Okay, now we have motivation. Now the question is, how do we calculate these automorphism groups? Okay, and you can ask more generally, how do you calculate automorphism groups of blowups of P2? Because let me write this slowly here.
Is there an issue for automorphism of conic bundle?
Yeah, there are some issues, especially characteristic 2. Going to be a bit tricky because you use hyperelliptic curves somehow to understand automorphism or minimal automorphism groups of conic bundles in characteristic 0. And I'm not sure exactly what happens in characteristic 2, but surely it will be a bit more complicated. Also in the other characteristics, let me mention this. So for example, if you look at Hertzebruch surfaces, then the P elementary abelian groups that act in characteristic P on Hertzebro surfaces, they are unbounded in rank. So because you have a G8 to the N action on the nth Hertzebro surface, so you have lots of P elementary groups. So you will have large finite groups. And yes, yes, yes. But the interesting thing is for so in Cremona 2, you have this over every field, because somehow the dimension of the GA that acts becomes large. So you all have the FP value points of GA, and you have a big product of GAs. So even over a finite field, you unbound elementary subgroups in the Cremona group. And
single GA,
also for finite fields. So I think it's more complexities. Yes. Okay, so let me write this lemma because it's also interesting if you want to understand automorphisms of more general blowups of P2. So if you're interested in automorphisms of cobalt surfaces or something like that. So you should understand this. So if you have a blowup in endpoints, there's also to fix notation, so I write definition here. So in endpoints, then as we all know, right, the Picard group of the blowup is generated by a strict transform of a line and the exceptional curves. Okay, so the CI are the exceptional curves. And we can also describe the canonical bundle, canonical divisor, with respect to this basis. It's -3 times, -3 times a line, and you have contributions of the exceptional divisors. Okay, and then I define the lattice EM as the orthogonal of the canonical divisor in the Picard. And well, you see, of course, automorphisms of Y will preserve KY. So they will preserve the orthogonal complement. So they will act on this KY perp. Okay, so you get a natural group homomorphism psi from automorphisms of Y to the orthogonal group of this lattice EM. And at least if M is in the relevant range for this talk, so you can replace the orthogonal group by the Y group. Okay, even the Y group if M is at most 8. Okay, so for Del Pezzo surfaces, we get this psi, which goes from the automorphism group of the Del Pezzo surface to the Y group of this root lattice. Okay, and one important observation here is that this tends to be injective, right? If you blow up enough points, this is injective. So if at least 4 of the PI are in general position, let me add one more page. Then the only G that preserves all the exceptional curves is the identity. Okay. In particular, this tells you that. So this is a bit more, a bit stronger than what I'm going to write, but in particular, it implies that psi is injective if M is at least 4, and points are in general position. So in particular, psi is injective in this case. Okay, so this is just generalities on automorphisms. Blowups. Can you read what I write? Should I write bigger? A bit bigger? Okay, good to know. Okay, so now we have the definition of the Pezzo surfaces, right? We have this basic lemma, and I gave you some motivation. And in the main result, I said that if the degree is at least 5, then determining automorphism groups of the Pezzo surfaces is easy. And I prepared a small table for you. Okay, so this is the example, which should appear in a moment. Okay, very good. Okay, so this is, I assume X is a del Pezzo, which is not P1 cross P1, because we all know the automorphism group of P1 cross P1, right? So this is only for the blowups of P2. And let me just go through this quickly. So we have degrees 9, 8, 7, 6, and 5. And well, there are blowups in 0, 1, 2, 3, or 4 points in general position. But these are only 4 points, right? So I can put them into nice positions. And since you don't blow up many points, you can describe all the -1 curves and the complete configuration of those -1 curves on this del Pezzo surface, right? So of course, if you don't blow up a point in P2, then you have no -1 curves. But also these blowups are not too hard to describe. And the last one is I have to explain this because the first 4 pictures, they're not the dual pictures, right? The 5th picture is a dual picture. So I write the dual graph of the -1 curves. And this is the Peterson graph, okay? And now you have those graphs of -1 curves, and now you just look at them and you determine the automorphism groups of the graphs. And well, the first ones obviously have trivial symmetry. The third one you can flip, right, left, right. The fourth one, it's a hexagon, right? So you have the hexagon symmetry, and the symmetry group of the Peterson graph is well known to be S5. Okay, so how to determine the automorphism groups of those del Pezzo surfaces? Okay, again, P2 we all know it's PGL3. Okay, and then if we blow up 1 point in P2, on the blow up we have only 1 -1 curve, which means every automorphism of the blow up descends to an automorphism of P2 that fixes the point, right? So this is just automorphisms of P2 that fix the point. It's just this subgroup of PGL3. The third one is similar. I mean, you have the symmetry of the graph. Everything descends again to P2, and you have the symmetry which swaps the 2 points. So you get the stabilizer of the 2 points, which is this group I wrote here. Okay, the first interesting case, a slightly interesting case, is the fourth one, the Pezzo surface of degree 6, right? Because the graph has D6 symmetry. You look at the 3 points in P2, and they only have S3 symmetry, right? So you only get an S3 symmetry of the graph, and it's unclear whether you get the whole D6. But certainly you have, let me write this, you have the torus also, right? I'm saying you have S3, let's write like this. But you have more, because you have the standard Cremona here. Let's say we map x0, x1, x2, 1 over x0, 1 over x1, 1 over x2. Standard Cremona involution, it's a rotation by 180 degree. Maybe let me zoom in a bit. Right, you have this rotation. You map this -1 curve to the opposite -1 curve down on P2. It would correspond to mapping the point to a line, which you're not allowed to do in using automorphisms of P2. But the standard Cremona realizes this. Okay, so you have one extra involution, and you already had the group which had index 2 in D6. So if you add this Cremona involution, you get D6 here instead of S3.
Let's see.
Yes. So I can tell you the S3 will be replaced by D6 in a moment. Okay. Okay, and then let me just quickly go through this part. Yeah, to the fifth case. Okay, that's very good to know. Maybe I'll just point. So we have the 4 point, right? So we have the S4, which is realized by automorphisms of P2. S4 has index 5 and S5. So if you want to say that the automorphism group of this blown up surface is the whole S5, you have to find one additional automorphism. And I mean, you just see it that the Cremona involution, it also fixes the point 1, 1, 1. Right? So it lifts to the blow up in 4 points. So you have this additional automorphism which doesn't come from P2. So the automorphism group of X has to be S5. Okay, so by exploiting some of the symmetries of the curve configurations and some known automorphisms, you get an extra automorphism of order 5 that maybe you don't see immediately. Right? So there has to be a Cremona of order 5 that's less than those 4 points. So this is what I meant by easy. And you see all of those families, they are 0-dimensional families, right? So in all those degrees, you have those isolated examples of del Pezzo surfaces. And the real story begins in degree 4. Okay. So now let me talk about del Pezzos of degree 4, 3, 2, 1. Right. So the plan of the talk is now very easy. I just go through the remaining degrees and explain how you would calculate the automorphism groups of such surfaces.
This is characteristic free, right?
Exactly. Yeah, that's why I wrote this table, because all of those arguments you see, they don't use characteristic. No, it's completely fine. No problem. No. Okay, so this is why I isolated this table, because it's completely characteristic free.
Because you only need 0.
Exactly. Yes. And do it over spec C, I guess. Okay, but starting with degree 4, it becomes interesting, right? Because the surfaces have moduli. Okay, so let's try to understand degree 4. Okay, we heard this before, and most of us know that a quartic del Pezzo X in P4 is the base locus of a pencil of quadrics, right? So it's the base locus of a pencil Q of quadrics. Okay, so let me emphasize, this is characteristic free again, but if you want to write normal forms, you have to assume characteristic different from 2. So the discussion will be characteristic free, but I will give you a normal form, just so you know what to think of. Right? So if the characteristic is not 2, you can simultaneously diagonalize the 2 quadrics that generate this pencil, so you can write the equations of the del Pezzo as something like this. Right, AI some numbers and in K, and they have to be distinct, otherwise the surface is not smooth. All AI distinct. A discriminant of Q. Okay, so it's a polynomial on P1 that vanishes if the element of the pencil is singular, and it has a simple root if the quadric over this point has co-rank 1. And well, in characteristic different from 2, what you would do is you take the symmetric matrix, take the determinant, right? And that's the discriminant. In characteristic 2, you have to be a bit careful, because if you this kind of operation, this discriminant you get is always 0. So you have to do it formally and divide by 2, essentially. And that's what I call half this, what people call half discriminant. It's Kneser's half discriminant. But it's really just the usual discriminant that it vanishes if the fiber over this point is singular. Okay. And well, I stated earlier that Dogashev and Duncan studied this case. And it's classical if the characteristic is not 2 or say 0. It's that this delta has 5 distinct roots. So the smoothness of the base locus implies that delta has 5 distinct roots. Even in characteristic 2, yes. So this is why I write these 2 names, because some are in characteristic different from 2, right? You see it immediately from the normal form, because you see immediately, well, if not all the xi squares that appear in the equation of your quadric, the quadric has co-rank 1, otherwise it has co-rank 0. So you immediately see the five singular members of this pencil. But in characteristic 2, you have to be a bit more careful, but you get the same result. Okay, so this is a set of 5 points. Also, if P is equal to 2. Okay. And now we're interested in automorphisms of these quartic del Pezzo surfaces, right? And now we see we have associated to a quartic del Pezzo, we have a pencil of quadrics. So the automorphism group of the del Pezzo, it acts on this pencil of quadrics. Okay, so you can find a subgroup of the automorphism group of the del Pezzo, which I denote like this. So those are automorphisms of the pencil that act trivially on the base of the pencil. Okay, and of course, the action on the base, it has to preserve this delta, right? So you go to the stabilizer of delta inside PGL2. And now you have to observe that this map is actually surjective. Okay, and again, this is easy to see from this normal form in characteristic different from 2, but it's also true in characteristic 2. Okay, so this is why I write those two names again.
Can you explain the kernel and say what's automorphism?
Those are automorphisms of this pencil that preserve every member of the pencil.
The total state.
Of the total, yeah. Yes. And well, now you stare at this normal form if you want, and you calculate this kernel, and you get its C2 to the 4. Yes, maybe I should do this. It's always C2 to the 4. And again, it's also C2 to the 4 in characteristic 2. But if the characteristic is not 2, look at this normal forms. You see the singular points of the singular members of this pencil. They are exactly the 5 coordinate points. And saying that you act trivially on the base of the pencil means you fix all the 5 coordinate points. Right? So the kernel has to act through the diagonal torus. And once you know that it acts through the diagonal torus, it's very easy to see that you can only change signs essentially. Right? And then you get a C2 to the 4. But that's also true in characteristic 2 with a different normal form if you want. Okay, so you see we have essentially complete description of the automorphism groups of quartic-Del Pezzo surfaces. Because the kernel is always C2 to the 4. The image is always the stabilizer of 5 points in P1. Okay, so this means to describe the automorphism group of X, we have to determine the stabilizer of those 5 points. Okay, so I will write down the most symmetric ones, but maybe let's first think about it for a moment, right? So it's in PGL2, and it's also in S5 because we have 5 points on P1, right? But it cannot be the whole S5 because if we fix 3 points in P1 with the identity, right? So the simple transpositions cannot be in this stabilizer of delta. So somehow the biggest thing you can expect is A5, okay? Because you cannot fix 3 points. Okay, and now if you're in characteristic 0, you try to come up with a symmetric configuration of 5 points in P1. What you do is, for example, you take the 5th roots of unity. It turns out this is the most symmetric configuration of 5 points. And for the stabilizer, in this case, is the dihedral group of order 10, right? You have the action by multiplication by 5th root of unity, and you can invert. Okay, so this is D10. Okay, but in positive characteristic, and this is kind of the slogan of the talk, we have more symmetries, right? Because if you allow your characteristic to vary, how do you come up with a very symmetric set of 5 points on P1? So you look at the F4 rational points of P1, right? So P is equal to 2. Look at this set. Somehow, if you let the characteristic vary, this is the most symmetric thing you can write down. Okay, and then we all know that the stabilizer of this is just PGL2 over F4. Okay, and this is A5. Big and characteristic 2. Okay, so maybe one last word about this story of quartic-Del Pezzo surfaces. So you can, I said earlier in this lemma, right, that we have this injective map psi from the automorphism group of the Del Pezzo surface to the Y group of the root lattice. And in the degree 4 case, the root lattice is the D5 root lattice, right? And the Y group of the D5 root lattice. Maybe let me write this here. Compare the Y group of D5 is C2 to 4 semi-direct product with S5. Let's react on. So if you want, you can see this exact sequence, the split exact sequence, as a geometric incarnation of the Y group of D5.
These morphism groups are geometrically reduced, so there's no scheme.
Very good. I wanted to say that earlier, actually, but let me scroll up. I hope it will come. So I wrote in the lemma, right? I wrote this psi that if you blow up at least 4 points in general position, that this psi, the map from odd Y to the orthogonal group, is injective. But this holds true on the level of automorphism schemes. And so if you have vector fields, you have those rigid curves. The vector fields are tangent to those rigid curves. So the vector field will contract to a vector field on P2. And you have no vector fields on P2 that vanish at 4 points in general position. So it's a scheme theoretic version of this. Okay, so, but that's a good observation, right? So all those automorphism groups that will occur will be reduced. So it's a completely discrete thing. Okay, so now I'm cheating a bit because I promised you I would go through the degrees, but now there's degree 3 and there's a lot to say about degree 3. And because our work was on degree 2 and 1, what I want to do is just skip the degree 3 phase.
So the divide group, the automorphism group as in excluding the divide group, no?
Yes.
Is there some interpretation of this additional
So if you want, you can. So this part, the stabilizer of delta, it's also the stabilizer of the point on the quintic del Pezzo that you blow up, because you see you have this S5 action on the quintic del Pezzo surface, and you can interpret the quintic del Pezzo as a modular space of 5 points on P1, and you get this natural S5 action. And those 5 points on P1, they correspond to discriminant. So you can interpret this in terms of, well, you have an orbit of length 2 on the quintic del Pezzo. So there's 2 ways of blowing up. I don't know if this answers the question. The more conceptual explanation of those automorphism groups. Okay, so degree 3, I think I would completely skip for time reasons. There's of course interesting story. As you can imagine, in characteristic 2 and 3, you have more symmetries. And for example, a Fermat cubic in characteristic 2 has a very, very large automorphism group. But I will not go into the details here.
Characteristic 0, not everything is realized.
Yes.
Characteristic 2 and 3, like a lot more things.
Yes, exactly. And then you can also, there's a classification of conjugacy classes in Y groups, and you can go through the classification of conjugacy classes and try to describe the surfaces that realize the conjugacy class. But then
characteristic 3, it's somehow the oldest thing for degree 3. I think less than realized, but much more than realized.
There's several phenomena that somehow play against each other. If you have lots of wild automorphisms, it's somehow harder to realize. So either you have a very, very symmetric, like the Fermat cubic, or the surfaces that realize this automorphism become singular. Somehow there's several phenomena. It's not clear a priori what happens. Yeah.
Assume it's smooth, not just regular.
Yes, everything algebraically closed. Okay, so let's talk about degree 2. Okay, in particular, I want to state some characteristic free facts about the Pezzo surfaces of degree 2 that also hold in characteristic 2. So we saw earlier in the week that this is a bit of a subtle case, right? Because I will write in a moment, those are double covers of P2, and as you can imagine, double covers in characteristic 2 are a bit more complicated. But I'll state a list of characteristic free facts, and then we see what happens. Okay, first of all, the Y group. Right, so we have the automorphism group in the Y group, so we have some very rough a priori upper bound on the size. Okay, so the order here is 2 to the 10 times 3 to the 4 times 5 times 7. And the anti-bicanonical system of a del Pezzo surface of degree 2, it gives an embedding of X into a projective as a quartic. So this is always fine of the form. I just write down a general smooth quartic. Looks like this. So vanishing of W squared plus F2 XYC W plus F4 XYC. Okay, so you always have this equation that will appear in a moment. Okay. With fi of degree I, of course.
So this is really for anti-canonical algebra. So you also have
Yeah, you also have the minus the map to P2. Yes. Okay, so this is the next point. So if you look at the anti-canonical map, it's the projection onto x, y, c. So projection to x, y, c is given by the anti-canonical system. Okay. And now the reason why in the beginning I was very slow when I said the path surfaces are always sorts of P2 is because you can use this blow model to count the number of -1 curves, right? So we do not have to care about this 2 to 1 map. We can just count the -1 curves on X. So the set of -1 curves on X it always consists of 56 curves. Okay, it's a very easy count using the blow-up model of P2 in 7 points, right? You have the 7 exception devices, you have the 7 cubics, and then you have a 20. A very simple count and a characteristic-free count. Okay. Yeah, exactly. Like positive roots or something. Okay, and now we have this description as a double cover, and this description is again canonically, this double cover is canonically associated to X, right? So the automorphism group of X acts canonically, it's compatible with this pi. So we have an exact sequence. So there exists an exact sequence, let me write it like this. Automorphisms of X over P2 to automorphisms of X. And now let me write G. G is by definition just a quotient. So G sits inside PGL3, and G is the group of automorphisms of P2 that live to this double cover. Okay, and now so this is standard theory. And now a couple observations on this. Well, you can ask again about kernel. Right? In characteristic 0, we know the kernel is always C2. It's a double cover. It's very easy. Turns out the same is true in characteristic 2. So this pi, this double cover is always separable. So you always have the deck involution even in characteristic 2. It always exists. Yeah. That this kernel odd X over P2 is generated by an involution, and this involution is called Geyser involution. We have this canonical element in the automorphism group of X. And now you can ask, what is the image of this Geyser involution in the Y group? So how does the Geyser involution act on E7? It's always minus the identity. Well, the reason is because quotient has rank 1. So quotient E2 has to be rank 1, so you have to invert everything in E7. Okay, now let's take these two observations. I'll add a third in a moment, and go back to those -1 curves on X. Because now you have this double cover, and the fact that the Geyser involution acts as -1 on E7 tells you that the Geyser involution there's no -1 curves. So the -1 curves are interchanged in pairs, meaning that you get a map here to lines in P2 that split on the pi. And then this is 28. So you always have 28 special lines in P2 in all characteristics. Yeah, I wrote up there.
Where?
Next to the 56. Okay, so there's a 2-to-1 map to lines that split on the pi, and there will be 28 lines because the map is 2-to-1. Okay. And well, the third observation is that I group of E7, because E7 has odd rank, right? So the -1 minus the identity has determinant -1. So you get a split of the Y group into plus minus the identity and special orthogonal group of E7. Okay, so we have the special structure of the Y group of E7. And why is this interesting for us? Because it means that the sequence star splits. Well, because what does a splitting mean? It just means that you have a preferred lift of every element in the quotient, right? And as a preferred lift, we take the element that acts with determinant 1. Okay, so you have this nice canonical splitting, if you want, of this short exact series. Okay, maybe let me say a word about the proof. It's not so hard to prove this separability, right? It's clear in characteristic different from 2. And in characteristic 2, if it's not separable, it's purely inseparable, right? So it'd be purely inseparable double cover of P2, but then this purely inseparable map, it's an Étale homomorphism. So this X would have to have the same melodic homology as P2, but it does not, right? It obviously does not. And the reason why I tell you this argument is because it also works if X is slightly singular, but has P-carring not 1, right? So the same argument tells you that if you have a canonical del Pezzo surface of degree 2, you have this double cover of P2, then this is separable unless the P-carring is 1. And then even in P-carring 1, you can classify. And there's only a couple of exceptions. I think there's only 4 surfaces for which this fails. So almost always this map pi is separable. Okay, and well, this part is completely characteristic free, but at some point I have to make this distinction between characteristic 2 and characteristic different from 2.
So line splits, you don't want to call them by tangents.
I'll come to this in a moment. Yes, this is a very interesting question. Okay, so now I want to do this. Do a parallel discussion of the characteristic 2 case and the characteristic different from 2 case. Sure. I will explain in 2 minutes. Yes. Okay, but this is exactly, so those 2 questions are exactly the reason why I split this discussion. Okay. So we have different from 2 and P equal to 2. And I want to be very slow here because I think it's important to understand the differences. Okay, so we all know, right, if we have this quadratic, if we have this double covers, like W squared is plus F2W plus F4 is 0, we can always kill the F2. Right, so if the characteristic is different from 2, we can set F2 is equal to 0 always. Okay. And in the characteristic 2 case, it's the complete opposite because this F2 is never 0. Because that's what I wrote in the lemma above, right? They said pi is separable, but this is the same as saying that F2 is non-zero. Okay, so pi is separable. Okay, now to answer the first question, now once we killed F2, it's very easy to see the branch curve in characteristic different from 2, right? Because when do we have unique square root? Well, if and only if the element you're taking the square root of is 0, so if and only if F4 vanishes. Right, so the branch curve is the vanishing locus of F4. This is the branch locus of pi, always smooth. Right, so this branch curve is always smooth because the Pezzo surface is always smooth. This is well known. Okay, let's go to the other side. Okay, so let's ask the same question, right? So we have this equation W squared plus F2W plus F4 is 0. And for which values of X, Y, Z do you have a unique solution W? Well, if and only if F2 vanishes, right? Because if F2 vanishes, you're taking a square root and square roots are unique. Right, so the branch locus has a similarly simple description. It's the vanishing locus of F2. So this is the branch locus. And let me note here, well, we all see it, right? It's a conic, but more interestingly, it's not always smooth. Okay, so this is maybe more unexpected. So note, this is conic, too small. It can be singular, even non-reduced. Okay, so for example, let me give you a very simple example. So you take w squared plus x squared w plus xc cubed plus y cubed c. Okay, and it's very easy to check that it's actually smooth. It will appear. It will appear. Okay, so we have this description of the branch locus, which is different. So this is one of the reasons why I distinguish those two cases. Okay, and then the next question was about bitangents, right? So this is another interesting question you can ask. So when does a line split? So a line L in P2 splits under pi. Well, let's be very slow here to understand really what's going on. This happens, of course, and only if the F4 becomes a square when you restrict to L, right? So this happens if and only if F4 restricted to L is a square. And well, geometrically, of course, this means that L is a bitangent. L is bitangent to P. Okay. And now let's ask the same question in characteristic 2. When does a line split under this separable double cover? So a line splits under pi if and only if. Now let me check. Okay, so this is more tricky. You do the calculations. You try to see when this line splits. So you have to understand this arbitrary cover. You restrict to this line L. And turns out that the condition for splitting is the existence of a quadratic form on the line, such that F4 restricted to L is S squared plus SF2 restricted to L. Okay, so you can calculate this. It's not so hard, but it's a bit satisfying, right? Because how do you describe these lines? And so these lines we call fake bitangents. And well, now the question is, and this is open, I guess, how to have a good, so to give a good geometric description of those lines that split. Because, well, certainly they're not bitangents to the branch conic, right? Because for a con, you have this conic, either you're tangent or you're not tangent. And there's many tangents, right? So the question is how to geometrically characterize those 28 curves. Now you can try to go through theta characteristics, right? And characteristic 0, what you do is you have this quartic, and you can describe the bitangents as the 28 odd theta characteristics. Now on the other side, you could go to the ramification curve over the branch curve, which is a singular curve of genus 3, and try to describe some theta characteristics there. If there's time, I will talk about this at the end. But well, we have no solution so far. Even in that case, you have 28, right? It's a bit unclear what this 28 is.
So it's the same number somehow.
Yeah. So somehow you have conic with additional data, right? You have the conic together with the restriction of F4, and somehow there has to be a count of the 28.
In mixed characteristic, are those fake bitangent specialization of bitangent?
They must be. Yes. But I mean, you can choose many lifts, right? And they have the same specialization somehow. Okay, now let's come back to automorphisms. Okay, so how to understand automorphisms of this separable double cover of P2. Let me again do it slowly in characteristic different from 2, and then explain what fails in characteristic 2. Okay, so an element of GL3 induces an automorphism of P2 that lifts to X. This is easy if only if you send F4 to a multiple of itself, because then you send F4 to lambda F4, right? And then you scale W with the square root of lambda, and you get a lift. Okay, so G upper star or G sharp if you want, of F4 is lambda F4 for some lambda. Well, and this just means, right, that means that G bar preserves the quartic. And then, well, you have this classical step, right, that this quartic is canonically embedded into P2. So automorphisms in G are just automorphisms of the quartic. Okay, so you have OB1 is equal to omega B, and B is non-degenerate. So G is isomorphic to the automorphism group of B. Okay, so this means that in characteristic different from 2, it suffices to understand this quartic. And well, then you can imagine, right? Then the classification the cubic somehow, because you have this hypersurface of a certain degree, and you use invariant theory to classify the groups that can act. Because then you have classification via invariant theory. Okay, and this ends this side of the story, because now, okay, now you have to work, and it takes a while, right? But it's clear how you do it now. Okay, so let's look at the other side. So again, let's start the same way. We take an element GL3, and we ask when does it induce a G bar in G. Okay, now you do the calculations, and you realize it's not enlightened. Okay, so you get that G upper star of F2 is lambda F2, because of course you have to preserve the branch curve, right? So you have this. But now this trick that I said. Yes, yes. But it's still infinite, unfortunately, right? Exactly. So, but now this trick that I used on the left, right, that I said I just scale W with the square root of lambda, it doesn't work on this side. I have to understand what this G does to F4. Okay, and this is again tricky. So you have, there exists an H, now a quadratic form on P2, such that now you do the calculation, H squared plus lambda H F2 plus G upper star F4 is equal to lambda squared F4. Okay, so you have this extra condition, which is again hard to understand. But as Dan observed, this is already very good, right? So we preserve this B. So at least, because B is non-degenerate, right? So in the worst case, it's a double line, but even a double line is not contained in a line. So if you act trivially on a double line, you're still the identity on P2. So G is in the phase of B in PGL3. Okay, and now the big question we spent the last 5 minutes on is how to understand G. Okay, and the idea here, I mentioned this before, is that you look at the pre-image of B on the pi, right? If you do this in characteristic 0, you just get a first order neighborhood of the branch curve, essentially.
So B is our conic.
B is the conic, yes. And the idea here is you study the pre-image of B. Since, of course, an automorphism of P2 that lifts to X, it induces an action on B that factors through an action on this R, right? Because it comes from upstairs. So since odd X to G factors through R. Okay. Now this R is very interesting. Let me make a table. To give you a taste. So first, let me write down the possibilities for B, right? This is simple because I'm talking about normal forms for conics. Okay, so we have 3 cases. So we have B smooth, say, yeah, I don't have to write the equations actually. Okay, so we have B smooth, B union of 2 lines. And B double line. Okay, so the picture on the right, like this. think it does, right? So you just have the strange point. Yeah, maybe only one. Right? So it's still a conic. But let me remove this. Okay. And now you can try to understand the pre-image of this P. Right? This R is now an inseparable cover of P, but it's usually also reduced, but it's always singular. Okay, so let's understand this R. So this R, in this case, in the first case, R is int, and it has either 3 cusps or 1 cusp, and then A4 or an A6. Okay, so that's the picture. You always have arithmetic genus 3. And so the picture here is you have this R with the 3 cusps. Okay, this is picture. This is an X. This is P.
Because the branch looks R is not reduced, or you take reduced.
It can be reduced. So this is interesting. It can be reduced even. So it's just the only thing you can say is it's a cyclic cover of the branch because it's an inseparable cyclic cover. Yes. And yeah, this is important. So you have to understand the non-reduced structure as well. Here in the second case, R is reducible and reduced. And you have 1 A2 on each component. And here, R is non-reduced, but irreducible. And you have 1 A2 on the reduction. Yes.
Why is it always singular?
Well, why is it always singular? It's because, so this is a bit more complicated to explain. Because if you have cyclic covers, inseparable cyclic covers in characteristic P, they will always have singularities over the vanishing locus of a certain differential form. And well, you calculate Chern classes, for example, and you see that it has to vanish somewhere. So here you get somehow this R always has 3 singularities. Its differential form always has three zeros. Okay, so the picture here is something like this. And here this. So the common feature of those is the R is always arithmetic genus 3. It's similar to this branch quartic in characteristic 0. So this is how it goes curve somewhere in characteristic 2. Yes, exactly. Because you see, if you have the W squared plus F2W plus F4, if F2 vanishes, this. Yeah. Yes. Okay. Okay, now the approach is again a bit clearer, right? Because now we have some marked points on this del Pezzo of degree 2, right? So some of the story is very different from characteristic, different from 2, but you have additional structure. You have a stratification on the moduli space of degree 2 del Pezzo surfaces, and you get a lot of marked points on those del Pezzo surfaces. And of course, having marked points is very good if you want to determine automorphism groups. For example, if you look at the picture, what you see is in this generic case, the G has to be an S3, right? Because it acts on the conic with 3 marked points, right? So in the worst case, it fixes those 3 points and it fixes the conic. So you see, you get some more geometric approach to this question, which is not just calculation. Of course, if you do the details, then you have to realize those automorphisms. So you have to really work. But you see, there's a lot of geometric structure, and I wanted to show you this. Maybe one more thing I want to say is, well, you know that in characteristic 2, a smooth conic has a strange point, right? We had this on the board before. So if you look at the strange point of this smooth conic, which is canonically associated with the Pezzo of degree 2, and so you get a canonically marked point in P2 associated to this del Pezzo. So on the del Pezzo of degree 2, you have a canonically marked 2 points, if you want. So what you can do is you can blow up those 2 points. And if you blow up the 2 points, you get a rational elliptic surface. So you get an action of the automorphism group of the del Pezzo of degree 2 on this rational elliptic surface. And you can study the fibration there to understand the automorphism group. So there's lots and lots of geometric structures that you can exploit here. Okay, so I'm out of time. So someone mentioned earlier that for cubic surfaces in characteristic 3, this phenomenon happens that you have smaller automorphism groups than in other characteristics. In degree 2, the same happens in characteristic 2 because you have this additional structure. So you get smaller groups. Okay, but one interesting group, let me write this. One interesting group that appears here is C2C to the 4. It will act in this case if you have an A6 singularity, so you have a conic with only one mark point, so you have a GA action somehow on this conic, and the C2 to the 4 is inside this GA. And this is interesting because in characteristic 0, if you have a C2 to the 4 acting on a del Pezzo, it comes from the quartic del Pezzo. It comes from the C2 to the 4 that I wrote earlier. But this is not conjugate in the Cremona to this other C2 to the 4 action in characteristic 2. So this is a new conjugacy class, but it's the same group that we already saw. So there's some interesting phenomena. And now, because I promised this, and then I'll stop. In degree 1, let me write two things. So there exists pi to P1, 2. Right, 2 to 1. So they're always double covers of quadratic cones in characteristic 0 branched over sextic. In characteristic 2, in the generic case, a twisted cubic that passes through the vertex. So you have interesting geometric structure. Again, you can study again ramification curve. And in particular, what I wanted to say, this pi is always separable by the same argument as in degree 2. So you always have a Bertini involution associated to a degree 1 del Pezzo surface. And again, this generalizes to canonical del Pezzo surfaces. And this degree 1 case is harder than degree 2 for 2 reasons. First of all, P112 is more complicated than P2, right? And sextic is more complicated than the quartic. But also this nice little trick that we used in degree 2, that the Y group splits in this minus identity, a semi-direct product with special orthogonal group, doesn't work in degree 1 because E8 has even rank, right? So you can show that the Bertini involution acts as -1 on E8, but -1 it has determinant 1, right? So you don't get the splitting. So there exists a non-split sequence 1 to C2 comes from the separability, right? To automorphisms of X to G. And well, so you have to do 2 things, right? So you have to again study this ramification curve R, study the singularities, you get some marked points, and you have to calculate the automorphism groups using the geometry also. And then you have to solve this extension problem. Right? So this usually, the sequence does not split in general. Okay, so the several points where this becomes more complicated, but it's doable. Okay, so let me stop here. Thank you.
Just in this last case, so you're not using the next maybe 4 anticanonical. You're only using the anticanonical and bi-anticanonical.
Yes. Yes.
The others don't help.
No, it becomes too large.
Elliptic operation.
Yeah. Yes, we use it. Yes.
It can be quasi-elliptic.
No, it can never be quasi-elliptic. No, this one cannot be quasi-elliptic somehow because this map is separable. So yeah, maybe I can show you something. So you can somehow see the nature of this elliptic vibration in terms of the branch locus, right? And again, you have this cubic, and this cubic in the generic case it's a twisted cubic, and in this generic case you will not have cuspidal fibers in your vibration. But if this cubic degenerates, you split off some lines through the vertex, right? And the fibers of the elliptic vibration, they are the preimages of the lines. And over those branch lines, you have cuspidal fibers. Okay, and so you understand very well from the geometry of the branch locus, you can understand the singular fibers very well. So you have up to 3 cuspal fibers, but sometimes that the branch locus becomes a triple line through the vertex. So you have one very bad cuspal fibers and all other fibers are smooth. Very interesting vibration.
Up to 3 cuspal fibers is a feature of.
Now I think in different characteristics you have more.
Yeah.
Right? So yes, 6. Yeah, 6 out. In characteristics, yeah, it's a special feature somehow because you have a wild conductor. Yeah.
Yeah, so it just adds much more.
Yes. Yes. Yes.
Could I have types of these cuspal fibers?
It's just everything is integral somehow because there are no -2 curves on the del Pezzo. So if you blow up once, you don't produce -2 curves because you blow up the base point of -kx.
So if you have 3 cuspal fibers, then you have no more degenerate fibers.
Yes, 3 cuspal and the rest smooth. Yes.
What is the largest?
Very nice. Okay, so here the biggest group. I prepared this. The biggest group. First of all, it appears in this case. Where, I mean, you can imagine it appears in the triple line. And the biggest group is, okay, let me write it like this. So it's an extra special 2 group of order 2 to the 7. And the semi-direct product with C15. Okay, so this is the whole odd X. Okay, maybe I should explain this notation. That this means this one it sits in an extension. This. Is it? I don't know if it's a Heisenberg. Yeah. Okay, so I want to say it's an extension of a 2 elementary group by a 62 group, and the C2 is central, and it's also a Fratinian commutator subgroup. And this plus stands for the Arf invariant of the quadratic form on the quotient. And somehow you have a quadratic form on the C2 to the 6 that determines this extension. And well, elements where the quadratic form vanish, I think they lift to something. They have lifts of order 2, and the one where the quadratic form doesn't vanish lifts to something of order 4, and you have this classification of those extra special groups in terms of non-degenerate quadratic forms in the quotient.
It's just that you have Z2 over 2 to the 6th power, you split it into 2 subspaces, like it's a space of 3. 2 Z over 2 to the 4th power, and fix some pairing between them, and then define the completer pairing.
Yeah, I think so. I think that's one way of doing it.
How does C-mod 59?
Yeah, so this is very interesting because this group, so this group, the person is group of I think a 2-dimensional family of degree 1 del Pezzos, and in the generic case, some of this acts on the base, and then it degenerates to an action that fixes the base, because those vibrations you have here, they have super singular generic fibers. You have a quaternion automorphism group of the generic fiber. And somehow this 2 group degenerates. So the action somehow changes. And C15, it has this, so you have a C5 action on the base through 5th roots of unity, and you have a C3 action on the generic fiber. Because let me write this. So if E is super singular elliptic curve, then the automorphisms of E in characteristic 2, some are quaternions, and you have this C3 here, and this C3 and the C15, and you have a degree 5 action on the base.
So any details happen to other characters,
Yeah, there are some interesting things that happen somehow. In characteristic 5, I think we had the largest group because this thing that Kostya mentioned, that you can have 6 cuspal fibers, right, in characteristic 0. But you can imagine if you put the 6 cuspal fibers in symmetric positions, you can get again more symmetries. And then characteristic 5, we put them at the F5 value points of F1, of P1 set.
So you can go Pezzo 2.
Yes. Yes. You get a PGL2 of F5, yes.
Which is again big fact.
Is it a, is it a, I don't know. I never remember those.
I
Isomorph.
think it's again 35 it's non-standard actual 6 points.
Mhm.
I guess.
Good. Yes. And then there's also the automorphism group of the generic fiber there, which is a C6. So it's some extension.
How about cubic manifolds or quantitative taxonomies? Instead of the action on lines, you can take action on the line.
Yeah, I don't know.
Issue is
Even the actual final set is hard to analyze.
Let's thank Gebhard again.